lock in, please. Here we go. All right. So, yesterday I mentioned that there is an equation that we are not going to use. And it is true. We are not going to use it. Actually, I realize I'm taking one step ahead of myself here. I do need to start here. Video. Watch this video. Come on. Do the thing. There you go. Everything in life requires a commentary. All right, here we go. You guys don't get to see this yet because you were talking too much and you didn't earn it. All right, so we'll see how. We'll do that on my thing. Okay, so here's the conversation of the last video. What particular portion of this particular chapter does that apply to? That last video that you were watching at. What happened there? What is the system? What way would you explain that? Using stuff from this chapter, I will give you a hint. It is not yesterday's conservation of momentum, okay, which you might think leading into today. But no, discuss. What is the topic that last video was showing?
That's just like when you have force tension.
X versus center of gravity.
I know it's 6,000. Don't make me throw things. You can tell them that.
Why would you throw things?
Okay,
Well, yeah,
there's
he's like leaning forward.
it's a dumb joke.
What
right?
happened today?
Probably nothing really particular. It's just 6 hours. I have to deal with people's crap and dumb decisions and like dumb comments all day long or whatever. And having to deal with one of them is not bad. When you have to deal with like the 80th one or whatever, it's like, hey, we're doing really complicated stuff, and we know that you're working through it really complicated like out there, but we're gonna mess with your head and kind of rage bait you with particular jokes in one. All right, what's the topic? What is the topic that we are discussing? Moment of inertia is not it. His moment of inertia wasn't changing.
Center of gravity.
Angular
Close.
velocity.
Combine the two things you just said, and you're there. Sum of a little closely, but sum of torques equals not zero in that case.
Is not
Inertia.
Correct. The two ways that you could have said this kind of quickly are as follows. You can either A, say dynamic torque systems, basically meaning it's angularly accelerating, or the other thing that you could have said is Newton's second law for rotation. Sum of torques equals I alpha. Looking at that system, yes, you saw that there was angular acceleration, so let's take a step back and look at it from the perspective of sum of torques. How many forces are acting on this particular gentleman as he spin round, gravy, right, round, gravy?
2.
No.
1 if you look at it.
No.
3.
Oh, wait.
3 is
yeah.
correct. And I wanted the actual
I see.
number. I know what you were about to do, and you are technically right from that particular perspective, 100%. What are the 3 forces acting on him?
Gravity, normal, and then
Probably a random force of leaf blower. Right now, of course, to Elia's particular comment a second ago, and I believe this is right, correct me if this is not where you were going, force gravity and force normal are not going to cause torque. Why? No, that's
because
not why.
if they're at the center of mass.
Okay, gravity is at the center of mass. Yes, gravity is, so it's not going to cause torque. Normal runs parallel, so it's not going to cause torque. I believe Elia was going to comment that if you look at it from the top-down view, then you don't see either of them. Is that fair? Correct? And what is the only force that you see in that particular case? Force of random. Now, you will also note from watching the video, apologies people online as I talk about this, the direction, this is going to represent the leaf blower in this case, that of course how he did it, right? He did not put the leaf blower straight behind him. Obviously, if he had done it straight behind him, would this be a torque problem at all? Nope, because of course there would have been a force at a parallel portion, so that would have probably caused him to accelerate, assuming that he can get over friction, not anything there. Next, so he put it out here. Why did he put it out here? Not because it's perpendicular. Out here, let me counterbalance here. He could have put it out here and aimed it that way. Would that have caused him to rotate? No, so putting out here gives us lever arms, what I was looking for, and then yes, obviously he didn't go that way, he went this way, so that it was perpendicular, and thus that force caused torque. And it was the only force causing torque, so torques were imbalanced, and what happens to a thing when torques are imbalanced? They will angularly accelerate is what I'm looking for in that particular case. Cool. All right, now, yesterday I said that there's an equation that I don't want you to worry about, and that is true. We are not going to mathematically worry about it, but I realized backtracking here that we should probably discuss it a little bit. okay, as we continue this. So, what is the definition of momentum? Mass times velocity, correct. All right. Just as a heads up, remind me once again, how many of you are coming to physics 2? Okay, for you guys real quick, that's actually not the definition of momentum. It is and it isn't. It's not wrong. It's not wrong for anything that has mass. Okay, but just a quick aside, because this will help me when you guys come to physics 2 and you have this conversation later in the year. The actual definition of momentum comes off of this guy right here, the impulse momentum theorem. The actual proper definition of momentum is that when you change it, it causes force. The reason for that particular discrepancy is, answer me this. Can light cause force? Better question. Does light heat stuff of yours up?
Yeah.
Cool. So does it change the speed of objects in you? Yes. So does light cause force? Yes. Does light have mass? So can we use that definition for light? No, we can't, but we can still use this definition, that when you change the momentum of a particular thing, it causes a sum of forces, blah, blah, blah. That's why that is the proper definition for momentum, not that one. This still does work for anything that does have mass, though, so yay. All right, now off of that, I want to remind you of this conversation right here as it relates to the two football players running into each other, when we used one versus the other, right? When these two collide with each other, if we just look at person on the left, whatever they were, Jonathan or whoever, who was the other one on the left? Jonathan on the left? Who was on the right? Patricia was on the right or the left? Jonathan was on the right. You guys are getting really worried. I don't know. I mean, it's fine. You can lie to me right now if you want. There was no such thing as Jonathan. You guys could just kind of gaslight me at this point. It's my point. Okay, so if Jonathan, we'll deal with Jonathan because I like the name, on the right, gets hit by a force, we dealt with this guy. Why? Because there's a sum of forces on him. But if instead of just Jonathan, we look at the pair of them, due to Newton's third law, what was the sum of forces on him? 0. And when that's the case, then there would be no change in momentum. And simply put, there has to be no change in momentum in order to use this guy, because that's literally what this says. Hey, everything at the beginning equals everything at the end. If everything at the beginning equals everything at the end, how much has changed? None of it. So in other words, you get to use this one when this is 0, and this is only 0 when sum of forces is 0. Cool? I say that to draw the parallels. Now, back to yesterday. What is angular momentum? Moment of inertia, angular velocity. Very good. And the equation that I brought out to you was this one for this guy, conservation of angular momentum. But I gave you a bunch of examples, and I realized I didn't give you a means to figure out when that works and when that doesn't work. For example, in the very first video you watched today, is his original angular momentum the same as his final angular momentum? No. So that conservation of angular momentum would not work in the first video today. When is what? So I'm going to explain this equation that goes right here. Now, as a heads up, I am not going to use it mathematically, and neither are you. I just want to use it so that you know when you get to use this one. Just use analogies. Guess what the impulse momentum theorem for rotation is? So when do you get to change angular momentum? Nope. When do you change it? When there is a sum of torques. This was perfectly represented by the first video we watched today. Was there a net torque on him? Yes. Did he change angular momentum? The reason we will not worry about this video is similar to this guy up here. If you remember, this is actually just a rearrangement of this guy. And as complicated as this chapter is, I don't want to give you two things that essentially do the exact same thing. So if there is a sum of torques like his first system today, as you mentioned, this is what you're going to be using. Yes? Okay. Now, so Spainhour, when are you telling me I get to use this one? It's the same analogy. In order to use conservation of angular momentum cannot change. In order for angular momentum not to change, there must be no sum of torques. So in a full circle way, we're back to sum of torques equals to 0. What type of problems have we already done where sum of torques is equal to 0? Bridge problems, right? What's the only major difference between what we're doing now and bridge problems? Things are actually moving right now. There it is. So, to represent an example that I showed you in class of this exact same idea, it's this. If I was standing on this spinning thing, people online, I'm standing on this spinning thing, okay? And I just perfectly balanced right here, would you ever expect me to start spinning? No. So what do I have to do then in order to start spinning? We'll be a little bit more careful. Specifically, not just any force on it, because if you came up, you were really mad at me, and you shoved me in the center of the chest, would I start spinning? No. So, I'd have to put my arms out here, and you'd have to push them that way, aka you'd have to cause torque. Or if I wanted to do it for myself, I'd have to reach out here. I couldn't push just any which way, I'd have to push that way. And then I start spinning, right? So as I started pushing, was there a sum of torques?
Yes.
Did my angular momentum change?
Yeah.
Yes.
But, as I currently spin around, is there any sum of torques on me now?
No.
If we ignore friction, no. Actually, technically there is because of friction, but let's ignore it. So since that's the case, is there conservation of angular momentum? That's when you get to use it. The other example we saw that I described yesterday was the ice skater doing the same thing. Or the other example that I'm going to show you now is a diver.
There is something about the element of risk and danger
In the 80s. Look at his hair.
looking up at Rick Charles, 24 years of age.
Just wait till they zoom out. It gets more
Nervously, all of them looking
I know that's way too high.
They're going to zoom out. It's fantastic because I like watching people's faces while they do it. And it's going to keep zooming out, and it's going to keep zooming out when you think it should stop.
knees very heavily taped.
Told you. Everybody was like, okay, but no, but okay.
His girlfriend Linda. Look at the face.
No, that's like forever. He's not diving in the lake. No.
A lake would kill him.
Look at Rick up there, eyes closed.
Watch him. See, he's scared
Bucket of
too.
water that's right next to the pool that's perfection.
I don't care about practice, brother. One wrong is
And there's Linda praying for him down below.
Why are the witnesses do it like 75 miles an hour?
Why are these tape? I'm surprised the rest of them is tape.
That is the lake. That's a bougie pool. That is so fishery.
I really
Got it. Really bad.
Yeah, it's insane. All right, no, it's not a bad video. It's because I'm recording at the same time. It's the video's has been really terrible. All right, so. All right, now it is a little bit harder, I will admit, to see this one versus like a standard dive where a person's spinning a whole bunch. I'll try to find a better video of that. But answer this question in your group real quickly. When is he following dynamic torque, or when is his angular momentum conserved? Discuss quickly. It shouldn't be a long question. Hopefully it's a very easy question. If it's not an easy question, we need to discuss it. Take 20 seconds, hopefully you got the answer. So when is it dynamic, and when is let me say that differently. When is angular momentum conserved, and when isn't it in his situation? Specifically when he's moving, not when he's standing there. Because yes, when he's standing there.
Like whenever he's got it nice and tight, and he's spinning and then flipping and then arms out, that whole thing.
All right, let's see what you got. When is conservation of angular momentum not going to happen? When he's what? No, before that. Actually, it's obvious. I'm looking at think of the very, very beginning of his motion.
Oh, yeah,
When he starts jumping. Here he is. Yes, he's going off the diving board. Does he just jump straight up? Would it cause him to rotate if he jumps straight up? No. What he does, of course, is he lets himself fall out in front first, and then which way does he push with his legs? Up. And what does that do that we're talking about right now? It causes torque. So is there a sum of torques on him while he's pushing? Yes. So is his angular momentum changing in that moment? Yes. Now he's in the air. Is there any net torque on him while he's in the air? No. There's a force on him, gravity, but of course gravity is applied at center of mass. So does it cause torque? Nope. So is his angular momentum conserved while in the air? Which is why when he gets closer together, he of course spins faster, and he gets further away, he spins slower in that particular regard. Cool beans? Cool beans. All right. All right, so you guys are fine. You guys have done a good job. I'll show you the fun one from yesterday. Remember how I showed you that if you go too fast, the forces conversation, you have to take too much more force to stay in the circle? So, of course, if you get propelled by a human, there's only so hard they can push. But if you were German and decided to use a moped instead, that would cause a crazy amount of angular acceleration, requiring a ridiculous amount of force. Requiring a ridiculous amount of force to stay in the circle. And if you don't apply the necessary force to stay in a circle, what do? If you don't have the force to stay centripetal acceleration, you follow Newton's first law, you go straight, right? I don't know. Theoretically.
You post don't look bad. Is there a person sitting on this
Oh, that's right. I forgot. Hold on.
Is there a person sitting in the merry-go-round?
This video may be inappropriate for some users.
The president today.
All right. Gotcha. Just go to my personal account.
Yeah, I think so.
Copy this.
We know. Man.
Over here. Copy that. Copy that. Stop it. What are you doing?
No, what are you?
No, I'm talking to me. I'm not talking to anyone but the
I
computer.
thought you were
I'm literally talking to me.
I'm like, no, what are you? I think we watched Disney Plus.
Do you want to watch Disney Plus?
We can watch
What is that?
I see this when I was watching it.
Everything's a physics movie. Life is a physics movie. Safety first. Make sure you get rid of your cigarette. You wouldn't want anything to come to harm. Answer me this question real fast. Was that conservation of angular momentum?
No.
Definitely not conservation of angular momentum, because what was happening? What's causing the torque? The moped. The moped's causing an insane amount of torque, and so yes, angular momentum is cranked up. And as we saw yesterday, the higher you crank angular velocity, the more force is necessary, and then at some point a human being does not have enough forces in their neck or even behind them to hold themselves in place, so of course they go straight, as you saw. All right, moving on. Let's move on to some sample problems today. My goal today...
Risk and danger that excites the crowd. And this crowd here is...
Cool. All right. So what I want to talk about first is there's some easy math that goes with this that you can see, and I kind of want to add a particular layer to it because it is relatively easy. Okay, the first relatively easy thing that we see is like when I was on this spinny thing right here, right? And the relatively easy conversation about it is the fact that Spain-Hours, or we'll just say moment of inertia Spain, because there's only one object right here. There is only one moment of inertia. So if it's the moment of inertia initial times the angular velocity initial equals the moment of inertia final times the angular velocity final. And of course, what you can show kind of non-mathematically is simply this. Just conceptually, you could say, hey, if moment of inertia goes down, and how do I make moment of inertia go down on the spinny thing? Okay, pull them in. Then what does this have to do in order to conserve angular momentum? Yes, has to go up in that particular case. Now, here's the wrinkle we're going to add into this conversation. You will see that math come up here again, so I'll leave it over there on the right side to reference that it is relatively simple. You just said it just a second ago, although some difficult concepts can come up. Linear momentum is also angular momentum from a particular point of view. So let's talk about that point of view.
We just stared into each other.
Okay, it's fine. It's fine. Watch. Linear momentum. So here we go. Okay, I will represent that right now, and I'm going to represent my linear momentum not changing. Here it is. I have a mass. I have a velocity as I walk across the front of the room. My linear momentum didn't change. Yes. Now you might make the argument correctly Why would we worry about this otherwise? Cool, there's my momentum going across. When you have to deal with angular momentum, you have to consider it in a circle, or like that there is a point about which there is a center. So imagine, if you will, I'll draw it up here, but I kind of want you to think of it more in person in physical space. Imagine that the center of the circle was here.
Yeah.
Okay? Now, or in here, it's there for this particular person. Number one, as I walk across the front of a room, in a way, am I going around the circle?
Yeah.
Yes. Yes, I am. Right? You're heading in the next direction. Okay. Now, this was conservation of momentum. You saw it. My momentum stayed the same. Angular momentum is also conserved here. Okay? So, let's talk about that from this perspective. Because sadly, while momentum, the numbers just stay the same, those don't. What equation should I use for my moment of inertia about that point over there? About that point right there? What equation should we use for moment of inertia? This should be arguably the easy one. It's just mr squared. Right? Because remember what we said. When do you use mr squared? Here's a reminder of when you use mr squared versus that whole chart thing. Here it is. If I have a cylinder, and that cylinder is basically orbiting or somewhere away from the center, always mr squared. Now if it starts rotating around itself, like that, or like that, now you go to the chart because not all of the mass is at the same radius. But here, all of the mass is at the same radius, so we would use mr squared. Yes?
Yes.
Because of that, though, r is the distance from the center to the object. What is happening to r, draw this up here, what is happening to r as I walk across the front of the room? It changes, is all I'm looking for, but yes, where is it going to be the smallest?
When you're right in front of the.
Cool. So let's talk about that first section as it's getting smaller. So my moment of inertia, therefore, is getting smaller, right? Angular velocity is how quickly I change direction around the circle, right? Where would I change direction the fastest as I walk around that circle? When I'm the closest. So in other words, when this is the smallest, you would expect this number to correspondingly be bigger and bigger. Yes? The system where this is going to help us is actually, we're going to go back to discussing, I thought I had it over there. Okay? We're going to go back to discussing orbit. So here's the sun, and here, that's not. Certainly it's not going to be to scale regardless of how I do this, but there's the orbit of the sun. Sorry, the orbit of the Earth, rather. Now, a couple things about this real fast. Okay, number one, the Earth does not actually go in a circle around the sun. Okay, it goes in what's known as an ellipse. That being said, if I were to draw this to scale, nobody would blame you for thinking it's an actual circle. Okay, the actual percentage difference between a circle and what we see here is ridiculously tiny. It's fine to think of it as a circle, but it is actually an ellipse. Okay, a couple of vocab words because they'll help you on the homework and for no other reason. When we are at the absolute closest to sun, this is known as the perihelion. Ooh, I think I did it backwards last hour. I need to tell them. When it is the furthest for the sun, it is known as the aphelion. All those are distances, straight up distances. Make sure I'm actually right on this, so I don't. If you're the wrong one, I want to tell you. Yeah, darn, I got it backwards for that. You're good. All right.
Thank you for having me.
So I'm going to make up some numbers right here that are ridiculous, and I know they're ridiculously small so that we can just do quick calculations. That's not the goal of today, to go through the math. When you do the homework, it'll actually give you the right distances and the right speeds corresponding to this, which are going to be somewhere in like the hundreds of thousands of meters per second. And meters is going to be at like 3 times 10 to the 8th and like 7 times 10 to the 8th. It's kind of ridiculous how big the numbers get, but that's not important right now. So I'm going to say the perihelion distance is 6 meters.
Oh, wow.
Too small, I get it, not the important part here, okay? We're going to say that the planet is traveling 10 meters a second. Again, too small, I get that, not the point, okay? This math will work regardless if the numbers are dumb, like what I'm doing right now, or if you have the legitimate numbers later on. The aphelion just needs to be bigger, so let's go with 10 meters. Or actually, I don't want to use 10 again. Let's go 8. Yeah.
We do 12.
Now, the first thing that I want to discuss with you is what variables each of these would be. Okay? What variable would 10 meters per second be?
It's VT.
That's a velocity, right? Now, since that velocity is not going to change, and you're right, VT is technically accurate. Since that V is going to change, I need to put a subscript on this. Your options are initial and final, 1 or 2, or if you have a system like this, you're welcome to just say velocity of aphelion. Sorry, this one's perihelion. Backwards of last hour when I screwed up. So the velocity of perihelion we're going to say is 10 meters a second. All right, what is 6 meters then? What variable would that be? R. And again, it's changing, so R at perihelion. Or if you, again, I don't care what subscripts you use as long as you're consistent. If you want to use initial and final, it's fine. I don't like initial and final here because obviously when you're talking about orbit, there is no initial and final. It's going to hopefully go round and around and around for a while. Okay, but if you wanted to use it, it's not going to hurt you. 1 or 2, that'd be fine as well. RP in this case is 6 meters, which of course means 8 meters is 8. Right. What is 8 meters? RA, yes. And what we're going to be looking for here is what's the velocity when it's out at the aphelion? One very important thing that you're looking at right there, which you might know, is like freaking none of those variables except maybe R-ish remind me of rotational stuff whatsoever. How do we deal with that? And more importantly, why do we deal with that? Why can't I just say this? Why can't I just say, hey, sum of forces is 0, so conservation of momentum? Are sum of forces always 0 on this object? Well, no, they're never 0. But, well, if in this situation right here, we learned last chapter, gravity's going to pull this way, which is just going to make it change direction, yes? But as you get over here, the gravity and the velocity start to go closer together like this. So does it only change direction? No, it actually starts to speed up in various areas as it comes in this particular way. And actually over here, once you've gotten this way, it starts to get away from each other, which actually starts to make it slow down. So no, momentum is not conserved. That being said, hey, here's my lever arm. Which way is gravity going to go? That way.
Right.
Here's my lever arm. Which way is gravity going to go? That way. Will gravity ever cause torque? So is conservation of angular momentum now a thing then? Yes. So let's come over here and do this math, maybe change a couple of subscripts and see the exact same thing. Now, actually, before we get too far into this, let's go back to the arrows in order to understand what is moment of inertia doing? Is moment of inertia increasing or decreasing?
It's increasing.
It's increasing, so what should angular velocity do? Should decrease in this case. So here we go. Instead of initial and final, I'm just going to change this to P and A. How many objects are there here? Just one? So I don't really need to say, I guess I could go the angular momentum of the planet at the perihelion versus the aphelion. But no, I say planet because the planet's not changing. So we'll just make all these P and all these A. But those variables are not what I was given. Yes? Okay. What's my equation for moment of inertia on both of these? What's that? mR squared. So this is going to be, this guy here is going to be mass of technically what object? planet. Why am I probably not going to put a subscript on it? Don't expect it to stay a change at all, correct? But times r squared, should I put a subscript on r? Because it's going to change. So we have the r of perihelion squared. Next, angular velocity at perihelion. I don't know it. But do I have an equation that associates linear velocity with angular velocity? Hey, if you'll remember, it's this guy right here, Vt equals omega times r, and therefore omega is equal to the over r, or in our case, we're just going to say velocity at perihelion over the radius at perihelion. You will start to see as we're doing this stuff cancel. We'll wait until the very end to worry about that. And of course, I'm going to do the exact same thing over on this side. We have the moment of inertia is once again mass mr squared times velocity at aphelion over radius of aphelion. Just the exact same thing on the right side that I did on the left side. All right, what cancels? Masses cancel, absolutely, because it's the same mass on both sides, and yes, it affects moment of inertia, but since it's not changing, it's not what's changing the moment of inertia. What also cancels?
Like the RP squared and
RP is going to cancel with one of the squareds up above, and RA is going to cancel with one of the squareds up above, leaving us with arguably one of the easiest equations that actually come out of it, and it's this. RP times VP equals RA times VA. So the velocity at the aphelion is equal to the ratio of the radiuses times the initial velocity. So in our particular case, dumb case, where I made up some dumb numbers, it was 6 meters over 8 meters times, what was it, 10 meters a second. So what happens to the planet's speed as it gets further away? It does in fact slow down. Now, like I mentioned before, the actual numbers in the planet, it is very, very, very close to a circle. So do we actually expect the velocity to slow down very much with the planet? No. Because the differences between r is actually, I believe it's something like 1% difference. So what happens to the speed? Roughly a 1% difference in our speed does change. How are we doing? Cool beans. All right. I'm going to remind, for the sake of the video, I'm going to remind you of some math that happened yesterday. Okay, I know that you guys did it, but actually Fifth Hour did not do this video yesterday, so anyway, for Fifth Hour, I'm going to show it real good. And it's a good review for you guys anyway. Here we go real quick, and you don't have to write numbers down. We're just going to do it conceptually anyway. Okay, here we go. We got a person on a merry-go-round. Here they are. Okay, we're given some radius of the merry-go-round, and the person starts right here and moves further away. So we are going to, quote-unquote, change it from last time. Okay. How many different, start with this. Why should I use conservation of angular momentum? This actually works even better than you did for Fifth Hour, given your quiz 2 days ago. What has to happen to this guy in order to cause a change in angular momentum? What do you got to do to change the angular speed of a merry-go-round? You don't reduce the radius of a merry-go-round. You push it. Where do you push it at? On the outside. So let's say I pick a spot on the outside, the right side. Which way do you push that merry-go-round so that it goes through? You would either go push it up or down. Right. Since nobody's doing that and there's just a person standing on the center, is there a net torque? So is there a conservation of angular momentum? Yes. So here we go. Conservation of angular momentum. Of course, the major difference between this problem and last problem is how many angular momentums were there in the last problem? How many are there in this problem? 2. All right. So here we go. We have angular momentum of, let's name the person different than yesterday. Why do you always do males? I mean,
Haley Bone.
Haley Bone.
Yeah.
Specifically Haley Bone?
Yeah.
Okay, all right.
I think it's like a unique name.
Okay, Haley Bone initial plus the angular momentum of what's the other object?
Landon Davis.
Okay, I know you guys know this. Hopefully this is in fact review. Okay, when we look at angular momentum, we should be able to spot whether or not things change or cancel. Okay, the angular momentum of the merry-go-round is based on both its moment of inertia and its angular velocity. Is the moment of inertia of a merry-go-round going to change? So why does its angular momentum change? Oh, change the word slightly. Angular. I know it's super pedantic, but it's super important to be that pedantic in this chapter. All right, so here we go. Haley-Bowen final plus the momentum of merry-go-round final. And like I mentioned yesterday, subscripts get annoying, so I'm not going to do Haley-Bowen. I'm just going to do Haley because it's annoying as it stands right now. Okay, yesterday I asked the question of do any of the angular momentums cancel? And in yesterday's problem, we had the person walk to the middle. So since they walked to the middle, did any of them cancel? Yes, because when they hit the middle, their total initial, there's a lot of words thrown around here, and I'm trying to be precise as possible. The moment of inertia of them is 0, and therefore there is, since Haley-Bowen is moving further away, will any cancel? No. What do you expect to happen to the angular velocity of this? Expect it to decrease, yes, because she's moving further away. Here we go. This would be moment of inertia of Haley initial times angular velocity of Haley initial plus moment of inertia of merry-go-round initial times angular velocity of merry-go-round initial is equal to moment of inertia of Haley final times angular velocity of Haley final plus moment of inertia of merry-go-round final times angular velocity of merry-go-round final. All right. Good review from yesterday, but for anybody online, here's what we just did. You fill out all the subscripts. If it's got the 2 subscripts on this, you just apply them to both of the 2 of them underneath so that you can just kind of brain dead, just put them all down on the page. The next thought, though, is which values are going to be the same so that I can get rid of some subscripts so that my math gets easier. Which things are the same? Moment of inertia, or be more specific? Merry-go-rounds is going to stay the same, so I get rid of initial on merry-go-round and final on merry-go-round because that number and that number are identical. What other 2 is now actually even more important to do now? What other things are the same?
Is it the velocity initial of Haley and velocity?
Angular velocity initial is going to be the same for both Haley and the merry-go-round because they're going to cover the same radians in the same amount of time. So cancel, cancel. And like I said yesterday, this would become important and is more important even today. Yesterday it was a nice mathematic trick. Today it becomes imperative. What can you mathematically do with these 2 values since they are the same on both sides? Factor them out. I'll show you why it's imperative to do now in just a second. And of course, we can do the same thing over here. The purpose of yesterday, okay, so cancel, factor, factor. The purpose of yesterday was find what was the angular velocity after we do all of this. And obviously, we usually have numbers up here. You can see where it becomes imperative right over here, right? Because we were going to be trying to find angular velocity final. That was going to be annoying if it was in 2 separate terms and thus has to get factored out. Okay, so mathematically you can easily see how this ends. This goes moment of inertia of Haley plus moment of inertia of merry-go-round times the angular velocity initial divided by that whole section, moment of inertia of Haley final plus moment of inertia of merry-go-round. And based on what you see here, do we expect the angular velocity to increase or decrease? Decrease because since she's walking further, these 2 numbers are the same, right? But when she walks further out, what's going to happen? This is going to be larger, and therefore, of course, you're going to go here. For the sake of people online, I know that you guys know this. Okay, what I usually highly suggest when you do these calculations is to calculate all of these moment of inertia separately to the side. You don't have to. You can plug and chug in there. You're welcome to. But just for the sake of people online, if you were going to use a moment of inertia of Haley, what equation would you have used? For the moment of inertia of Haley. mr squared. Why is it mr squared? Because she's not rotating around herself, she's at some distance from the center, so you have to use mr squared, right? And then, of course, unlike yesterday, we would have calculated the moment of inertia of final of Haley, but that was going to be an easy thing, because what's the only thing going to be switched about her? The radius final, and of course you would know all these numbers. And then finally, what equation do we decide for the moment of inertia of the merry-go-round? Let me ask you this, do we have to go to the chart, or can we just use mr squared? Got to go to the chart. Why do we know to go to the chart? because it's rotating around itself. Or yes, because it's a disk, and yes, that would be 1/2 times mass of merry-go-round times radius of merry-go-round squared. No initial or final on that guy, of course, because it would be a really bad merry-go-round if its radius was changing. All right, moving on. Last problem that will probably take us into tomorrow. I got really close to finishing earlier in 5th hour. I imagine I'll run out of time and have to pick it up very quickly at the beginning, but I got most of the way done, so I might need to hurry a little bit here. What I want to discuss with you is a combination of both of the last two problems. It's one in which there is linear momentum that also can be equated to rotational momentum, and you can see that easily because of this. Imagine I have my door over there, so I'll kind of go ahead and represent. Here's my door. All right, that's a terrible door. Okay, what perspective are we looking at?
Top down.
Top down. Okay, we're going to, once again, just try to make numbers easy so you can understand. Okay, let's go ahead and say the door is about 1 meter wide. I throw a ball at the side of the door, assuming it's not latched, and assuming that there's nothing holding it in place. What do you expect the ball to do after hitting the door? Probably bounce back. Okay. What do you expect the door to do? So what you'll notice is that the ball, linear momentum this way, change linear momentum that way. The door does not change linear momentum. What does it gain? It gains angular momentum in that particular process, so we need to look at what that needs to look like. Now, quick question, because it does matter for later. If I throw a tennis ball at the door, what do you expect the tennis ball to do? Bounce back, agreed. What if I had thrown Sally at the door? What would you expect Sally to do? Sally's probably going to keep going. Now, slower, but she is probably going to keep going, yes? Okay. So let's go ahead and throw a tennis ball today. You'll notice I put right over here, this will be the fulcrum, and let's start with tennis ball here, okay? Let's again use some relatively easy numbers, even if they're not quite accurate. This is way too big for a tennis ball, but also the numbers are a little bit cleaner. We say the tennis ball's mass is 200 grams, aka 0.2 kilograms. How fast do you want me to throw the ball at the door? 30 meters per second. Okay, so I'm tossing the tennis ball. That's not unheard of. That's not unheard of, about 60, 70 miles an hour. Okay, especially since it's a small mass of a tennis ball, so let's go 30 meters a second. All right, after the tennis ball hits the door, we do expect a tennis ball to bounce back, probably a little bit slower, so how fast do you want it to come back the opposite way? 10 meters a second is just fine. Okay, I mean, you can practice this yourself. You can see whether or not a tennis ball is close to the speed bouncing off, blah, blah, blah. We're not going to worry about that right now. All right. We're all going to assume, by the way, this picture doesn't fully show this, but that the tennis ball is hitting on the very outside of the door, okay? And of course, the door is completely free spinning. And what you'll notice in this particular case is that, weirdly, there is a torque here, okay? Because the tennis ball is going to cause a force which way? Down. But this is similar to the problem we talked about at the beginning of the class with the 2 people running. There is a force of the tennis ball on the door down. What does third law say? And it has to be at the same radius, so are both of them causing torque on each other? Yes, if you looked at the one individually, then there would be a net torque and it would change angular momentum. But if you look at the combination of the 2 of them, the net torque is 0, and we can conserve angular momentum. How many objects we got in this angular momentum problem? 2. What are they? So we got door initial plus the angular momentum tennis ball initial is equal to angular momentum of door final plus angular momentum tennis ball final. Okay, first step, easy step. One of these things is 0. Which one is it and why? Door initial, because? Be a little bit specific. You got to be careful with this conversation because unlike regular momentum, with regular momentum it's easy. Is it moving? No momentum. That's it. There it is. With this one, it can either be angular velocity or, like we saw in the last problem, it can be moment of inertia. Both can cancel them to 0. This is why I get this level specific. Why is the door canceling? No angular velocity, correct. All right, so here we go. If you struggle,
You can start off with the subscripts. I think you can start here. I think you can get here. Here we go. This is going to be moment of inertia of a tennis ball initial times the angular velocity of the tennis ball initial equals the moment of inertia of the door final times the angular velocity of the door final plus the moment of inertia of the tennis ball final times the angular velocity of the tennis ball final. Subscripts on this chapter suck. All right. Sorry for my harsh language. What's that?
Is there a worse chapter than
Subscripts, no. This is the worst chapter in subscripts by far. And honestly, maybe even between Physics 1 and Physics 2, this is the worst subject in. Because, like, basically, you don't need to use subscripts when certain things stay the same. And in this guy, like, almost everything potentially changes or is compared to something else. All right. So we'll start with the tennis ball. How do you get its moment of inertia? Well, come over here, look at the picture. Is the tennis ball going to be at some distance from the center? Guess where the center's got to be? Right over here on the fulcrum. So, yeah, so what equation am I using? Nope. mr squared, because it's at some distance from the center. So we have mass of tennis ball times radius of tennis ball initial squared. Arguably, by the way, I don't really need to say tennis ball initial, because we are looking at this right before the tennis ball contacts the door and after the tennis ball contacts the door. So what is R going to be for the tennis ball in both of those cases? What number? 1. Just the R to here, where it's making contact. Cool. Once again, what's the angular velocity of the tennis ball? Don't like that. Want to use linear velocity, so what do I need to do? This is velocity of the tennis ball initial divided by the radius of the tennis ball. We'll see some cancellations, but let's wait till the end. All right, what equation should I use for the door?
1/2 mr squared.
Correct, so L squared. You got to be careful with the L squared there. And the only major reason it's L squared, just as a reminder, is R goes from the center. L reminds you that when you're doing this, you are not just going from the center, but doing the entire thing. It is not 0.5 meters. It would be 1 meter in this particular case. Here we go. So this is 1/3 mass of door times L squared. I did forget to tell you that. I think I told last hour. I apologize. Mass of door, we're going to say, is like 20 kilograms. I think that's all you need. And the question, by the way, I should have told you this too. How fast is the door spinning when we're done? So coming back here, 1/3 ml squared is your moment of inertia. I'm going to leave omega of door final. I'm not changing that like I did the other one because that's what I'm actually looking for. How fast it's spinning. Now over here, we're practically going to do the exact same thing to this guy that we did over on the first side. This is mass of tennis ball times radius of tennis ball squared times velocity of tennis ball final divided by radius of tennis ball. Now, what cancels? And more importantly, what doesn't? Does mass cancel?
No, because we have 2.
Not. Yep. That's tennis ball, that's door, so no, they don't. Okay? Does this radius cancel?
With the squared, no.
The squared, yes. And with this guy squared, yes. Now this is a good spot to get off, and you can kind of get a sense of where this is, because actually from this point it's all algebra and you know everything else. We know the mass of tennis ball, we know the radius of tennis ball, we know the velocity initial of the tennis ball. We know the mass of the door, we know the length of the door, and we're trying to find omega. We know all the stuff on the right. I will add one thing. Because the ball bounces off the door, what do you have to do to this velocity at the end? It has to be -10, not +10 in that case. We will pick this problem up very quickly tomorrow so you can see a final answer. But that's all we got.